greet you as the participants and say a few nice words to all of us. Please, Professor Davis.
Dear ladies and gentlemen, dear conference participants, dear guests, colleagues, it is a great honor for me to have the opportunity to welcome you to our glorious city of Lviv, to greet you in the Lviv Polytechnic National University. It is beautiful assembly hall of the main building to our university in the 11th International Conference ICTERI. We are grateful for the invitation and the opportunity to take part in the organization and holding of the 11th Conference ICTERI. I hope that our information conference will not be worse than the conference which was held in the previous year. Another day, Lviv is famous as the city of information technology and tourism. In the past few weeks, Lviv has become one of the largest centers of information technology in Ukraine. According to the various census, more than 6,000 employers are involved into the information technology sector, and their number is growing every year. The pace of development of the industry in the last 5 years has increased on average than 20%, which range from 800 to near 2,000 people in this year. Industry need for qualified IT specialists. Lviv is also the city of students. More than 120,000 students study in Lviv, and it means that every fifth resident of Lviv is student. It is noticed that 10% students study in IT specialism. Nowadays, in Lviv, there are more than 26 higher education institutions, 4 levels of accreditation, 10 universities, 7 institutions, and 5 academics. Lviv Polytechnic National University is a leader in the training of IT specialists, both in number and level of training according to employers. Lviv Polytechnic National University is a leader in ranking of higher institutions in the number of applications from those who want to study at the university. Nowadays, Lviv Polytechnic National University has nearly 30,000 students who study in 64 directions and 120 specialties. For us, as university employers, information and computer technology are extremely important in education. I wish all participants a fruitful work, good results, new contacts, and acquaintance, exchange of experience. Also, I wish you good time for our hospitable city. Our city is really developing. We live in the city, the excellent part of which was included into the UNESCO World Heritage List, and requests from all over the world. You will have opportunity to see during planning excursion or simply by walking in the city center. I believe that you will leave you only pleasant impression and memory. Thank you very much.
Thank you very much. Our next speaker is the co-chair of the International Programme Committee of ICTERI. I'm happy to introduce Professor LVIV-UKRAINE, who will tell you a few words about the programme and the procedures and the quality of solutions and all the technical stuff, which is very important for such an international conference. Professor LVIV, you have the floor.
Dear colleagues, let me say some words on behalf of the committee, introducing our conference in this scientific part, this month part. So we have a lot of organizers, we have the committee of security consultants, and Maya and me, and I will show a short outline concerning our conference. So, the committee includes of mine conference includes 63 experts from academia and industry. It was 49 at the previous conference. These experts represent 17 countries. In 213 plus 15 countries. We have 4 external reviewers, 3 of them are from Greece and 1 from Ukraine. This picture shows some distributions between organizing committees, so we have surely large representation of Ukrainian experts, but as well United Kingdom, Austria, Germany, France, Greece, South Korea, Russia, and so on, and so on. Concerning interest to our conference, this is listings of site ICTERI.org, which everyone will use for information for registration and so on. And we have about 6,600 visits from the start of first call for papers till the registration ends. From these visits, almost half were unique visits, 133 countries were represented, and the map showed that almost all the group, and it's a Greenland here, and were represented by visits. 950 cities visitors were from, interested in our countries. So we have some diagrams which shows the increasing interest to ICTERI conference from 212 to 215. Accepted papers. This program committee works hard and the acceptance rate was indeed high. So every one of you passed from very narrow gates to, and all your papers are of high quality, because we have submitted 42 papers to the mind track, and only 16 of them has been accepted to be presented and to be published in conference proceedings. So the acceptance rate is 38%. Workshops keep this acceptance rate, and accept 29 of 77 acceptance rate became more stronger. So we have about 40%, and now we have less than 40% acceptance rate. Well, it's my pleasure to inform you that the conference proceedings has already been published at US org at volume 1336, and it's available online. You see the link, and 48 papers have been included in these proceedings, including Minecraft papers, including workshop papers, and proceedings are already at the site. About post proceedings, previous conferences, starting with 2012, continued with next year and last year, has been published at Springer series at different volumes. You see them at the picture, and we have agreement with Springer Publishing House to publish these conference post proceedings as separate volume. So what now? All your presentation will be will be checked by the steering committee. The best papers will be selected, and the best papers will be recommended for publication as post proceedings. It should be noted that this paper should be substantially revised and extended. We can't publish the same paper as conference proceeding and as Springer paper, so it should be extended and revised paper. After the conference, the authors of the best papers will be informed by steering committee and will be invited to present paper for submission to Springer. Short outline of the program. Program is available online at ICTERI. Program is available in versions to your packages, and program is built in following way. We have three parallels. Mine ICTERI conference run in one stream. Today 2 sessions, before and after the lunch, and tomorrow 2 sessions. In parallel, workshop takes place. So, for example, for today, yes, conference opening is now. After that, plenary session was first keynote talk. After that, 3 parallels, yes. 1 Minecraft and 2 workshop labs. And the finish, the last but not least, should be the talk of the day, the tutorial for today, and not least the tutorial, but welcome session. Well, we have tutorial session, we have 4 workshops, and we will have tomorrow IT talks sponsored and organized by the company. Okay, our distinguished speakers. We will have 2 keynote talks today and tomorrow in 2 sessions. First is by Peter Schiller, and the second is by David Esteban. And we will have a tutorial session, as I have talked already, by Ahmed. Well, it's a short outline, it's finished, and I hope I keep the time, and we wish you a very successful conference, very successful work and rest, and enjoy staying in here. Thank you.
so you can have what I
Yeah, you have 5 minutes.
That's fine.
As far as the organisers were very productive and swift, kept it sweet and short. We have 5 minutes to the lectures before the keynote session. I'm fine. Can everyone hear me well? No, not really. I can speak up.
Okay, that's good. It's not Good morning, ladies and gentlemen. First of all, let me thank to these my preceding speakers, and in particular the organizing committee of ICTERI 2050, to have done a wonderful job to make the conference possible this year. And I think, as I know, the papers and the reports you will see, in 6 days, it will become a very interesting conference. Now, I'm quite happy and proud to introduce to you Professor Klaus-Dieter Schäbe, our today's divine speaker. I know Klaus, I think it's about 25 years. Then I don't know exactly since when we know each other. He did his PhD in 1985 at the University of Bonn and received his Doctor of Science from the Brandenburgian University, Technical University in Cottbus. He then was with the Technical University of Clausthal in Germany as an associate professor for 5 years. And then went to the massive university in New Zealand for 8 years. Since 2010, he came, like 10 years ago, to Austria, and is now the director of the Software Center Hagenberg, which is a private outstanding research institute in Austria. Working together with industry, so it's funded by this industry, and they're doing party-theoretic, party application-oriented research. And that's exactly what Klaus' specialty from his education. He's a mathematician and quite technically working person, but his research, and he's not a big palette of papers, research papers. It's quite decent research, and we show that besides of his quite intensive formal work, he has also always looked at what can be applied in practice. Klaus-Dieter, you have now 65 minutes, and we are looking forward to see what you are presenting to us. Okay. Thank you for the introduction.
Thank you very much for the introduction, and thank you again more for the invitation to be here in this nice place in LVIV. It's actually my first time in Ukraine, and when I came here the first day, well, it was a bit like Austria, so but that's also something that from the past. Well, the place has changed. Belonging to different countries with its history. Well, I chose, I suggested 3 topics. Yes. Suggested 3 topics for this conference, for this presentation here, and the steering committee selected the business process 1. I hope you will be pleased with my presentation because this is a topic really at the outskirts of my interest. It's more the work of a larger team where I was really giving the ideas and the others had to do the work. And so the title is Rigorous Semantics and Refinement for Business Process. So I will talk a lot about modeling in this talk and what So I would like to start with a few introductory remarks concerning past modeling. Of course, we know modeling is one of the key activities in systems development. Has to, of course, be accompanied by other activities like validation, verification. So basically, we do some abstraction from informal requirements and then some formalization, then we check for validation, verification, whether everything is correct internally, but more important, whether it really is the model that was needed, that really captures what the application needs. And we also combine this usually by reification or refinement approaches, where we start with something on an abstract level and then try to add details, remove restrictions, and add everything that is needed to really come to a system implementation. So key questions when we are concerned with modeling here is always the adequacy of the model. Is what we are doing just the right approach for the problem, and it is not the right approach for pleasing our interests because we think that the particular theory we must use, this is like using the hammer for everything, doesn't work. We have to think about what actually is right. What is the depth of the use model? How deep can we go? Which levels of abstraction can we capture? Is it understandable to those who really want to work with the model afterwards? And also during the development process, if they come with the users come with some requirements, we put them in the model and then we explain, well, this is what we did, and the customer doesn't understand what we did. They may say yes, but at the end they will find out, no, it was not a yes. Can all features of the application systems be captured in the correct way, so the sound is complete, did not add anything there that is an assumption we made only, and actually it is not part of the system. I put something in. You see this often with students, they add attributes in some kind of model, but asking themselves where exactly they've come from. They were not specified. And this is semantics and pragmatics. Pragmatics is a very different topic, so we're going to talk about it. So it's semantics and model very different. And with respect to business processes in particular, I would like to say we have two axes here that we should consider. First is the horizontal integration of models. So we have complex systems and we have to address different aspects. So we take some meromorphic view, we have some model for maybe some control flow, we have a model for data that is involved, we have a model for the individual actors, their rights, their obligations, we have a model for exception handling, and so on and so forth. I did not even mention all of that now. So the key question is, do we have a clear view of what integration is? Do we know what we do when we integrate the models? Do we reserve, let's say, the information content there? And do we have then the means to support by means of the modeling also the process coming from the requirements down to the final system? On the other hand, vertical model integration I usually understand as a process going from abstract level to the concrete one, not let's say the part. So we have different models on different levels of abstraction. We have to get a clear notion of refinement and details, changing things, specializing, generalizing also. Having usually an M approach, n steps somewhere on a higher level, correspond to m steps on a lower level, usually in some of the areas we would become one. So key questions there are then ensure that the refinements, the changes we do during the process are correct, and that we are able to trace our requirements through the whole process, and finally come to execute the model. So, roadmap for what I want to talk to you in the remaining time here, so let's keep an eye on time here. simple model integration business process, emphasize on the control flow. Then briefly talk about message handling, event handling, just sketch this interaction, data handling and actors, so the agents the actors that are really doing the work, involvement of humans in the process. I will mention, and then finally also come a little bit to exception handling. Exception handling is just a reaction to interrupted events, as opposed to non-interrupted events, which are just part of the specification. So I title is semantics and refinement, so I will talk about semantics defining abstract state machines, which run the state-based rigorous methods. For the methods there, well, it's rather simple to understand, and I will give them to all your extent, so just use it and you will understand the problem. So then the horizontal, the vertical refinement, I will only mention a little bit about. Okay, let's start with the control flow, and let's start with a rather easy flow. Well, control flow basically means when we have a business process that we take this bird's eye view and want to see, okay, what happens, what is the starting point of the business process, what has to be done by the individual actors, in which order, under which conditions to achieve finally the particular result. And it has to be taken into account that in the whole process we have different tasks, different activities. Some of them are executed by the machine. So making some selection, if this is satisfied, then something else will be triggered, can be done by a machine. But most of the things are there, they are tasks that are then finally become tasks for a human to execute. Like you get something on your screen, you have to work on a particular order or whatever. So, how can we, in a very basic and very simplistic level, try to capture this control? So, we basically have a few core components. Well, first of all, we talk about activities. Activities refer to someone, being executing a particular task, compiling an order, writing a review, closing an application, or whatever is there, for which it uses some kind of interface to the system. We say this is just some task, just basically. Then we have, of course, the start of the event, and an end is just events. So we start at some point, and at some point we finish, so we reach the end. That's, well, very done. And third thing is we have to glue these whole things together. So we just use some gateways. And in these gateways, some of the information flow between the tasks and these activities, they are just bundled or they are split. So you get some gateway which you say, okay, from here on, if I'm here, I have to continue in 3 possible ways, or 2, or in any possible ways between 1 and 3. So we have different split gateways, we have different synchronization or joint gateways there, and I will just briefly have a look at the most simple ones are just exclusive gateways, so just go left or right, and corresponding join. Or the parallel one means go left and right. Okay, now just draw some nice pictures. So I'm from my background. Actually originally from algebra, so it means no pictures. But I have to make very simple pictures, just to start with the trivialities. Well, it's important to get the first example, the top one. So we start with the blue button on the left, blue circle on the left. Then we have exclusive split gateway like in don't like to use the same symbol for split and join, which is an overload of the graphical notation which confuses more than it helps. So make it sure you see triangles, so you see that something comes in from the left and then you have circles and so right. So you have exclusive, that's the X split there, means when you go there, the decision has to be made. You either move to the left or to the right, or to the top one or to the bottom. So you mean you get to the activity A or the activity B. One of them will be executed, and then you bundle them together. If this is finished, then you join there and move on, and you see that it's going to be the reactors. So very simple. Second one, we do the same thing with now AND symbols or parallel join, parallel split, parallel join. So we start there and we split, we go in both directions. So we do A and we do B, two activities there, and then if A and B have been completed, we join this again, and only if both have been completed, this gateway there will fire, and then we do C and then finish. So from informally, I don't have to do any mathematics to understand what it means. So third one, well, not so clear anymore, because we do not claim, and we cannot claim in business processes, that we have a nice bracketing structure, so like in a term-oriented language, everything that is open will also be closed. We can also have something like this. So we now have a parallel split there. As before, we do A, we do B in parallel, asynchronously, two units doing that task. Some problem here will be there. Now we come to this exclusive join. What does it mean? Well, if you go for BPMN, one of the famous or most popular methods for using business processes, we mean the exclusive join doesn't do anything. It just shifts lets the word go through. Means whenever A is completed, the gateway notice this, and you will execute C. Sometime later, B will be executed, and you have the same situation. Well, you find again, B is there, and will go through, so you execute C twice. This is the actual meaning. That's it. Well, now you have to decide, is this what you want to say with this exclusive join there? Well, by means of exclusive or you would mean, well, there should only be one coming from this process. That would mean exclusive or. If one is coming, yes, and the other one not, then do something. So if you want to enforce that C is only executed one, you have two possibilities. Either you refuse this whole specification as being incorrect, or you just say, okay, the first one comes, will be served, and then I notice the second time I don't do anything. So we have three different interpretations that we have to keep in mind. In the semantics, the well-defined semantics, we have to separate them. Or we, as with the third one, throw one from the other. Now, last example, and this is, hope I'm not boring you with these trivialities. Let's look at this more complicated diagram than there below. So again, we have this parallel split, we do A and B, and then later before doing C, we have to get something that B is completed and something coming from A is also completed. But we put an exclusive split there before. That means after completing A, we can decide either to go in the direction of C. So we come here, or we do D. And when we do D, C will wait forever. Someone says, I can't do my work because I need some more encouragement. Good excuse for some people working in administration. But nonetheless, it's not what we want. So it seems informally clear that this kind of control for specification is not correct. Okay, now let's try to start with very simple considerations and try to just formalize what we say. So using the experiments, what we do is just basically we use rules for if some condition is satisfied, then there is some action, and all these rules are executed always in parallel. That's the ASM is dealing with massive parallelism all the time. So what we do is we have states, and states are defined as custom structures, first-order structures, so it's a set of states or it's a set of functions. So we have a signature, and the signature has function signals, linearity, and when you make some distinction whether this function is maybe static, dynamic, so dynamic means it can be updated. So the location is defined by the name of the function, by the arguments, and then the value of this location is what defines the actual function. And we update these universal attributes or ASMs were originally called involving attributes when they were implemented by the correlation, but now we try to change. So basically, when we're doing so, we usually write some kind of formalized pseudocode that has defined semantics with case. So, why do we do this? Now, just basically look back. As I said, this is all asynchronous. So what we basically have is, we have one actor who is responsible for a sitting. Basically what this person does is waiting for the input to say, okay, I'm allowed to do my task A, and then I do it, and then I signal and break. It's any of these. And any of the other machine-controlled gateways, they just wait for some input. If the input is satisfied, there's something coming here, then I initiate the others. So help them, all these N, X, N, A, B, C, D, they work in parallel asynchronously, and they just wait for their conditions to be satisfied, and then they issue the trigger, the state change that will then allow us to do this. In doing this, well, we just have the freedom to look locally at any of these things here, and we can then look into the semantics of this business process, of this control flow, in a very simple way. First of all, we have several instances of processes that we specify by these control flows. They're all running in parallel. So just say for all P, here is a process, we run in parallel. Well, just formalize the same thing for everything. For all nodes, things, gateways, activities, and so on, they run in parallel. So for all F, which is a flow node, so these activities and the gateways, we execute them in parallel. If that means if their condition is satisfied, they fire, if it's not satisfied, they don't do anything. So what we then simply formalize is a little bit more to get the notion of states. So we have, as in our diagrams, we have then these incoming edges for each of these flow nodes. So we have, and we have outgoing edges. So we call them now in. This is basically the EPMN terminology that we preserved here. We could have said incoming edge, but it's called incoming sequence flow and outgoing sequence flow. And to model what I just said about how this control flow is done, we just use a simple token model. Well, to start with. So means when we start, we place the token here, we split, takes the token away, puts the token here. This one, when it's completed, puts the token here, this one puts completed over there. This one then decides the token goes here or there. One of them, and then this one has to wait for both being there and here. It's basically the whole idea in this simple code here. Getting more complicated later. Okay, so basically when we look at the formalization, that we have some kind of rule, ASM rule for any of these flow nodes. So I will node transition and just make it in the most general way that we need. We just have if the control start with a more general and when condition is satisfied and data condition is satisfied and the resource condition is satisfied. We don't have therefore anything to true in the simple form we have so far. We also get an operation, data operation, resource condition. So, means the execute that field that we have there is just the knowledge transition function. So we already defined this execute. Now, for the execute and the parallels with gateway control function is both the same. It basically says, well, we are able to do the split if there is a token of the incoming sequence. So it means the condition agrees that exists even if the incoming sequence flow knows based on the one, which can be there with tokens in the sequence no longer here or not, and here is this one. Well, we have already an example where we do. But if there is one, and in both cases, one part of the action, the control action, is just to remove the incoming token. Means remove the token is to choose one of the incoming tokens there that are in the set, there is not in the set, and then we choose for this token there, and then we just remove it from the set. That's all we have to say. And the only difference is then for speciality for what else we have to do, what we produce on the outgoing tokens in one case for the exclusive, the split gateway, we choose one of the outgoing sequence flows and we place one token there. This is the upper yellow part, and for the arrow one, which is all. Well, that's basically for the split gateway, so in general we just get this specification for the control action, control operation. Okay, now, well, then look at the join gateways. So it's the same game. So we look at the conditions and we look at the actions. So the condition is for the exclusive join control condition is that there exists a token on one of the incoming sequence flows. And for the parallel one is there exists one on all the incoming sequence flows. This is the only difference. It's even hard to pass the text there. And then in both cases, if the condition is satisfied, the control operations are the same because exactly one, there is only one outgoing sequence flow, exactly on this one. So this is still trivial. So I just, and then the incoming ones are. So I just skip this and you see it later. Now, let me come back to this already rather simple, trivial example with the exclusive join. And as I tried to explain in this simple third example there, we have to make a decision what actually is our semantics. So we have the specified semantics that we now did is one from and one incoming token will be removed, one outgoing token will be produced. Means if we have the situation from the third example I used, we get one activity then executed twice with different results, which may be what we want. So we just have to be aware that this is a semantics. Well, actually, I would call this not an exclusive join, I would call this an empty semantics because the exclusive join doesn't do anything. Well, what are the alternatives? We make a true join. When it means only one incoming token is considered, but all others are ignored. So the first one will be served, but that means, if I have the first one and the next ones I have to keep somewhere in my state track of there was a first time, and then notice all the others if they come to the roof, or I just pass through the whole graph and try to find out where are those and might still come to the roof immediately, which is a bit impossible because they may have some other split gateways in the way, and they may decide to go a different path when they go right. So better keep it in the state direction. All the other one is the true XOR, means you have to ensure, you have to prove that it is never possible that more than one works. Otherwise, the whole specification is ignorant. Three possibilities, we can specify all three of them, but we have to decide what it is. Okay, let me make a small digression about verification. So we would like to have some kind of properties that should be satisfied. So when we start a process like this business process, we actually want that at some point the task is finished. Sometimes we bring our administration, it's not satisfied there, but in general, we don't want to have that any flow nodes have to wait mutually for each other and block each other before they can continue. We don't want to have redundancy. Means that in the sense that each or gateway can eventually be fired at some point. When they're not there and they are never reached, they never have to do anything. And for the XOR join, if we have the third semantics, there we say we have to prove that also only one token may arrive at incoming sequence flow with A for each process. Okay, the first, look at the fourth, our simple examples that we have. So we have, when we start the finish day, this is satisfied for the first two cases and for the true XOR, the empty semantics, and also for the it is the same. That we terminate does not always work in the fourth case, as we expected. There are deadlocks, so we can prove all these things and say, we just make an example here how we do that. We consider the control flow in the first example, so anytime there's a more than one token, we have an exclusive gateway there. Will be split, then it will go to A or B, and then it will join together. And each pass starting needs to be both together and right side. We will continue. So you can formalize this a little bit more, but I don't want to go too much into this verification exercise. Now, okay. I hope I didn't bore you too much with this simple introduction. You may know these things these semantics may at the moment look a bit like an overkill. We don't need to really this. Well, apart from this, maybe this distinction of three different semantics for exclusive joins. Now, let's add another gateway. This has been discussed quite a long time in the business process community, and so finally, colleagues mine produce a solution and define the possibilities into their standard training. That's very difficult. Okay, now we may think about alternative gateways. So, and say inclusive join and similar inclusive split just corresponds to the logical OR in a sense. Inclusive join means synchronize all tokens that make arrive. So we start somewhere where you produce, you split, you create new ones, and at some of these inclusive gateways, you have to wait for all that may arrive to really arrive. And then you fire and remove them all and continue with one. motivating this is by, of course, you have an inclusive split. You get one incoming sequence flow, and then you select any subset of the outgoing sequence flows. 1, 2, 3, or how many you want to have. So 2 to the n possibilities for any outgoing sequence flows, and you take any of them and you continue with any subset of the outgoing sequence flow. Well, there is a subtlety there, so if you allow the empty sets with no outgoing sequence flow, then you actually add as an end node. Maybe this is not desired, but it's a particularity at the border of the whole thing, so we don't have to worry about this too much. Now, let me start again with some trivial examples. First one is when we modify the fourth example we had before, and now we replace this here, this parallel join by an inclusive join. Well, then it should be no problem anymore. Here we split, take A and B, and here we have to get this token coming to this inclusive join. And here, while A can go to D, then here is something that will never happen. There will never be a token arrive here. Means O is happy with this one, this token being here, no one else. Go trigger C, and then go to the end, and then one plus D. If this gateway is split here, puts a token here, then O is closed. It synchronizes all those that may arrive. Only it's no longer that static. We don't know at the beginning when, where the tokens are to be expected. And this will change during the work. In a more complicated example here, we make an inclusive split here. So we can take any subset of A, B, and C that will be triggered after this gateway. So we can take A and B, we can take B and C, we can take all three, whatever, we can take only one. So 8 possibilities if you allow the empty set as well. The empty set is trivial, then we are finished once we pass this. Don't forget the empty set. Now, these two here will be synchronized immediately and then split in parallel here and there. So it means when one of these here, or both that are executed, we will get some. If X has been selected, yes, it may be the case that something comes here. And then we can already go. Now, if we have 1, 2 here, then this is 5. If this is all that is expected. So we will get a G, and then we may come back via F to here again. So we have to make sure that everything that may around here will be used for firing and go to G, but not the F. Because the F will only happen once we have done this gateway. If we cannot wait for ourselves, this is not possible. Okay, so this is the, so how do we capture that? And that, the idea is very simple, and that goes beyond simply playing the tokens. We have to keep track of the information in the model which tokens may arrive. When, back to my example, in this case here we have for this is the only critical one. For this inclusive gateway, we have to keep track whether something can arrive here and something can arrive here. This code depends heavily whether we have A and what happens here. So how do we do this? Well, solution to in principle very simple. In addition to the tokens on the incoming sequence flow, we keep there for each of these inclusive join gateways. We keep a function flags. And the flag just says, okay, there can a token arrive. It may arrive. And as long as something that may arrive has not yet arrived, we can fire. So, and this is what is. And but what may arrive can be updated by the other gateways while there is. Let's just forget about this mathematical writing here. Just look at the example. So what do we do? Let's say we do this one here. Let's select all three ABC. There. Okay. Now in this split gateway, we make a decision. So A, B, and C will be executed, and that means for this inclusive join and that inclusive join, we have to set some flags. Everything that can be reached from. And for this one here, we have to notice here on this incoming sequence flow that something may come from here. We set a flag. Here we set that this may come from B, there may be something coming from C because we selected both. And here we have to also put there may be something coming from B and something may come from C. Now let's execute B and C, so the words of these fire here nothing changes because they can still come, and then we have a split here. So if this token comes here, then we say, okay, the token is there and it's the one coming from B and C both together because they have to be synchronized. So this one is this one. Now from this other token, the other flag, if this split gateway decides to go in this direction, but we place the token here, the flag will be removed. If it goes this way, while the token is there, the condition is satisfied, we can fire. When we continue this way, then we finally, if this one goes via F, then we get the token here. Also, once this has been fired, we put a flag here and say something like that. So it's just putting flags there, and then maintaining the flags to keep track of where we are. Very simple. It does not change our general specification for all the gateways. We still have a control condition, we still have a control action, control operation, and just the control operation includes removing of, say, setting these flags. Now, so this is basically what we say whenever we have a split gateway, then we set some flags, and whenever we have some kind of joint gateway on the way, or another gateway, we also update the flags. Yeah, this can be formalized in the same way with the mechanisms. Now let's go back to, we had these three different semantics for exclusiveness. The empty one, which we specified already, the one where we say it might be errorless, that we have to prove something, and the third one, the thing first come is the first to be served, and the others will be removed. Well, this is of course another application example for a flag. We set a flag there, which may come, and once it has come and it has been removed, there is no more flag there, then the next time it comes will not be to action. We need a flag, otherwise no action. Okay. One example. What I want to say with these incoming joins, by specifying that each of these gateways, each of these entities, basically specifying in the same way, control action, control condition, control operation, and then we refine the conditions. We can add a lot of things in our state that make very tailor-made special gateways that we can use. And the inclusive gateway is a very, very simple example where we use just these flags. One remark, if someone really is clever enough to see it immediately, in this specific case of the inclusive gateway, we could have got a solution without this. Because the condition we check here, we can also gather from looking, passing through the whole state where all the tokens are, and getting the live condition and then express this thing. The derived conditions and also. In this particular, in the case of the first come, first served, it's different, where we have to keep the information, and we get other examples where it's simply possible. Now, counters. Another way where we can add something more. So far, we did only the following that we say for create one. There's one incoming token, then there is one on an outgoing sequence per will. So this example, there are two generated by some kind of split gateway with the joint gateway with the empty semantics where we had some kind of parallels. Now, you can do this deliberately now. And you know a lot of examples where we actually do this. Well, look at the thing we all do. We're doing conference review. And usually we decide for each of our papers we get a certain task to be done, review the paper. And when we specify the edition, we say we want to have 3 reviews, or 4 reviews, or 2, or whatever. We specify them. One task will be not executed only once, but it will be executed several times. And we may even have that this number is the result of another activity that decides. Say, we've got 3 reviews, one of them is rubbish, and another. So we place counters. So instead of just using these tokens and flags, we also place counters on output, ingoing and outgoing sequence flows to add a bit more possibilities to it. Now, I want to talk about the verification. So, by having now these counters, we can also use counters for run counters. And run counters would be, now, let's not count that we need so many tokens, but let's count how often we have fired. So initially for a process we set the count to 0. Once we fire the first time, we move to 1 and so on. We just increase this count. And so, in doing so, we can now specify control operations that would do something different the first time, the second time, and so on and so forth. There is, again, there is one example for that, also complex gateway, where we just allow to make a distinction between the first time and the second time, and all the other times. Wow. This is like, you see you need something more, but then you put on a straitjacket and say, just take one specific case first and all the others. Well, I can count further than 2, and we all can do that, just putting a counter there for the runs, then you can specify whatever you like on the first and the third and the nth one is conceptual. Another thing that we can do at that point is then also dealing with priorities. By having all these tokens there, we then even decide some changes that are done depending on in which order the power tokens are behavior, which we said that first one activity is preferred over the other. Now, let me just explain this idea here. Another simple example involves some counters here and also involve priority joint. So here in this this inclusive not claim that we should put all these things in graphics. After a while, it's not very visible, very understandable. In fact, for this little example here. So what we say here, instead of splitting any subset of A, B, C, we allow now that we can have task 3 selected up to 3 times. And task B can be selected up to 2 times. And we can select C, so we can have 3 plus 2 plus 1, that's 6. So you get 2 to the 6 possibilities to choose something. Now it's not that. We don't distinguish the different ways. So this is what we use to split in our after this we go A and activities up to 2, and so on and so forth. And now, for the priority join game, we now can specify some complex conditions. Well, back then, so here what we have is this state where there may be some tokens arriving from A, some arriving from B. We also change this. Exclusive ones arriving from C. So different numbers here, and even some may come from F once we have 5. Now let's specify it. We say if there is one token from B coming, this gets highest priority. Means fire immediately B, regardless how many other tokens are there, and remove all the tokens that are already arrived. So this puts a lot of non-determinism in because it depends now on the time, how fast the other work has been done. Whenever something of type B has already been executed, then it has high priority. We don't care what A and C have done, because B will be well, if it's not the case, but there's one token coming from C, well then only fire if there's also at least one from A, if this is possible. So if there can be something. Or, but even if you have a high priority from E, in the case where there is already one token coming from F via the loop, so it can only happen once we got already through this gateway once. So the second loop, then wait for all possible tokens, we're back in the flag situation for the inclusive join, to arrive, and then fine. So you wait for really, this will be the last activity you do. And in all other cases, this is not the case, it's just actions, it's just a normal inclusive join. Okay, specifying things where we mean going through the same procedure again. We have a control condition, but the control condition now has several parts. But for each of these parts, we get a different control action. We just specify here informally text what the control action is, write them down in pseudocode and in ASMs. You have the specification of this priority game. Okay, so much for control flows. How much time do we have?
Oh, it's more than half an hour.
It's, because you said 65, I already understood. 45. Okay, messages and events. I will only briefly go through this. So we have the control flow. It's a very simple thing. We don't say what happens. They are how the activities communicate with each other and how other conditions, event conditions, will come to the game. Now, messaging. So messaging on a high level of abstraction, you can just simply say a message is defined by a sender, by a receiver, or several receivers, and execute. That's all we need. And basically, the goal here is to be just interested in the flow. We don't care about what the content is. So that's some kind of data content that gets to the goal of the abstraction. So, what is sending? Well, sending is nothing but a very particular activity. We send the message out to the recipients. And what is receiving? Well, it's also an activity. We have to take notice of messages that have arrived. By taking notices of messages that have arrived, we also react to a particular event, which is the arrival of a message. An event controls something has happened. The arrival of a message is if something has happened. So I can formulate a condition as an event in which the message has arrived, and then how the message is handled is part of the data operation, because I'm dealing with the content of the message. Or ignore it, or delete it, whatever I do. Let's forget about the and another thing, messages can be sent and received in a synchronous way, and be received and sent in an asynchronous way. Synchronous would mean the sender has to wait for the acknowledgement that the message has receive, read, before he can do anything. And then at the same time, the receiver or the receivers do something with the message. Asynchronous means I send and I don't get. This is the distinction we have to make. And so, we can, in our basic business process, people like to draw pictures. So basically, we're having these activities here. So we do some sending, and we just get some receiving there, and we just use some special symbols there, or we just write a message there, whatever we do. Now, what is messaging events? So, as said, the arrival of a message is, of course, an event you can take notice. And with events, something has happened. The main thing is not to specify that what are events. The main thing is to specify what are the events that are relevant. Not that task A at the beginning has been completed, maybe probably irrelevant for all the other activities, because they get it in order to manage the control flow. So we're not going to store anything about this event. But in keeping the process aware of all events means I have to define a language, have events, and so I have the atomic events like sending a message or receiving a message, and then I have all these logical and temporal connectives to create some kind of complex message, event conditions for this message.
Would you please switch to silent mode your mobile?
Okay. Now, there are several ways that can occur in connection with messaging. I said already the message will be sent, the message can be received, but there are also other events that will occur, and they can be taken into account for our specification of the language. Message can be delayed, message can be lost, message can be rejected, going back to the receiver, so I don't want to talk to you, I don't want to listen to you, so it just happens. The message is undeliverable, never reaches the receiver. All these things happen there. Whether you want to treat them in the specification is up to the specification. But the main thing, the message I want to get to you, I don't know whether it will be arrived, rejected, or whatever, but the message I send to you, as it was, is we can specify in event conditions whatever we want. The message from A has been arrived, and no message from B has come, then I do something. Or the message from B was sent 3 weeks ago and did not yet arrive, then I do something. All these conditions I can specify quickly. Now, how do we handle this? When we do messaging, then basically we have to look at the lower level, we have to look at the message pools, so any one receiving messages has some kind of mailbox message pool where you put the message in, so you can store the messages in there and you can handle them all the time, so you can put a boundary there, how much space you have in there, and so on and so forth. And then you can actually specify how the communication between messages. This is already going into vertical refinement of, say, the message protocol, how do we handle, say, the sending and receiving of messages with the pool, with the reactions to something that has not arrived, with rejection, and so on and so forth. Now, and the receivers and so on. Let's talk briefly about some other events. Well, I already said the event in the specification is something that has very plain term. This we use in our everyday life. And we can have internal events that refer to any activity, anything that has been done in the process, in the business process itself. So that can refer to all the type of nodes we have in the control flow. So we have the activities, gateways, start and end. We have messages and not mentioned recipients, but so continuous messaging. Now, let's look at the activities. What can we say about events in connection with activities? An activity can be enabled. Means the condition that has to be satisfied means the incoming tokens, they are there, and the flags count or whatever are there. The condition for being executed is satisfied. So the activity is enabled. The activity can be started. So the actor responsible for the activity has actually deleted the incoming, the tokens or the incoming sequence flows, and now has the activity in his pool of activities and does some work with it. Like the reviewers in our conference system getting the paper, they acknowledge I have received the paper, so they put it on the desk and let the dust be used. Or they do it, or they can be completed. And we can even think about other activities that we could do. We come to the actors a little bit later to make the model a bit more complicated. So we can postpone the activity. Well, if the actor has the right to say, okay, I've scheduled this work, but I postpone it, I first do something else, that will actually have to be done later. Do this like the Heinrich for his handling of applications for getting travel consent is he postpones the application for being allowed to travel after he has done finished the travel. So it's possible. You have to be able to handle it. You may be interrupted. So we started something, it was a complex activity, and then we said, okay, we have to do something else. Then we cancel. So we decided how to do it. We delegate. Delegation for the conference reviewing system is important information, like delay and so on and so forth. Put a lot of dots there because what we might think is relevant in the business process, information about activities, events associated there is somehow unlimited. Same with gateways. They may be waiting, they may be enabled, they may be fired, and so on and so forth. Start and end are events themselves. Messages and sentences we can also retry against time and so important. So these are internal events. Now next to that, we can have external events. External events refer to something that has been monitored on the outside. A letter coming from a customer, a complaint coming, a change of order, so a don't want a car in pink anymore, I want to have it in purple. So, like this. These things can happen, and they can be taken in, so we have to take all these events I mentioned. They are elementary. If something has happened, we just get a flag notion before the event is there. And we can then build a complex event. This event has happened, the other one has not happened, and both together have happened before another event has happened, but after 3 weeks and so on. So that brings in the last part for handling events. And events can refer to time. Time can be indicated. So using discretely a time model, also continuous time, clock, with problems of having the same clocks for all actors. That's a problem. And logical time is better. And so we can then also have time conditions and temporal relationships between events. So we create basically a very large evaluation if we for, say, event conditions. And I mentioned at the beginning also event operations. Event operations is basically just tell you which events do I consider relevant to the sort to be kept track of. Most of the events may be just totally relevant, depending on what you keep in memory. So the event condition and event actions. Now, okay, we have now started with control flow, maybe too complicated. We have, let's say, events, event conditions, event operations. We mentioned the messaging as a particular type of events there, but now let's look into interaction and data. Well, interaction looks actually at the activities that we associate with a particular actor. And what we normally also have to associate with them is what kind of data do they handle, what data do they need for this activity, what data do they produce. So, now the key idea is now that for all of these activities, you can just go a little bit lower, maybe or abstraction level, and specify that this activity is associated with a particular data. So just as you have an order processing system, someone gets the task to acknowledge and endorse a particular order, a particular travel application or whatever, data, and by means of this, you have to look into the data that is associated, where do you go, what are the costs, and so on and so forth, has to do something, just acknowledge or calculate some kind of total price, specify the account where it goes, and then store the data and then complete this action. So, I don't want to say too much about this, because this has been done ages ago, with dialogues associated with activities. Basically, all the data handling there is somehow a local view of global data. So you can now think of how you develop a database system, you do it globally, and then you specify the view, or you take the views associated with all the activities, and then you derive a new integration of the database. For us, at the moment, at the high level of the business process, what is relevant is just some data consumption. We specify the view that is needed for an actor to perform an activity, and we specify the data production, means what are the changes to the data locally and globally by means of the activity. And in doing so, I said we want to also keep in mind that we have to deal with some kind of consistency, with some kind of correctness of the process we specify. By means of data handling, we introduce a global view. global system. The database is global, underlying database. The view from individual activity is local. But if we have data conditions in all the activities, means that some activity that is in the control flow not linked to another activity may be indirectly linked via the data. And these conditions we have to be careful about. That's something that leads to another pitfall where we can get some kind of problems with the verifying process. So we have a global flow of data, so we have database objects or database there. The views are very defined on top of that, we define the dialog objects and the activities in the process. And we may even then for a particular activity bind of these activities to one. So this is all rather old stuff, and there's a paper from me in 2000, I think, where I do specify these things. Now, let me come to another aspect there, actors and roles. So we are now touching, since the beginning, control flow. I was mainly hardware things or VPN. If you look into something on data handling, VPN, it is very, very thin. They don't talk very much about it. If you talk about actors, then it is also very thin. The pool and lane concept, and that's it. But basically, when we talk about actors in any business processes, we talk about the involvement of the humans. And they do the main task, they do the main work. The rest is only doing these things together. So, when we talk about humans in a process, this is associated with responsibilities, with decision making, with executing some tasks, and we have to specify what are the rights of any actor, any role associated with an activity, and what are the obligations. So we have now basically we associate first at a very abstract level. Each activity, each basic activity is associated with an actor. And normally we just don't associate immediately an actor, we associate a particular role. So a role is nothing but a specification of obligations and rights. Someone can do a particular task. So we have to then look into how do we specify these obligations and rights. And without going now too much into the details of the logics, I would like to challenge you a little bit on a rather simple example, or actually a trivial example again. We have this control flow. So we have an activity B, then we have this exclusive split X equal to A over the direction of this empty join here, and this passes. So basically, this doesn't say anything more, so we do B, and then afterwards we do A or nothing. So A is optional. Well, from a control flow perspective, yeah, that's fine. That's all we will say. But from a deontic, actor-oriented point of view, the question is, so A is done or A is not done. Who decides? Who is responsible for making the decision? Well, what choices do we have? Well, look at this split A. You may assume, okay, in this split gateway, we evaluate some kind of data condition, say, and this data condition tells us whether A is to be executed or not. But that means, first of all, this is not a simple exclusive gateway. It involves a complex data condition. Nowhere specified in the diagram. We have to say that. So if the X is wrong, It's not something that should be a star, something complex there that is specified somewhere else. And in addition, you have to say where does the data come from? Somewhere B has to do it. This is one possibility. Often assume that this is the case, but it may not be the case. Second possibility, well, it's not the gateway of science. It's the B, deciding whether after I'm finished, A does it or not. Well, then you do this, B writes the decision into the database, and then the gateway can be done. Sounds a bit like an overload. So we have a gateway that actually does only what B has already done. Because the only purpose of this data is to trigger A or not. And then we also have to make sure that this is part. Well, it's possible, but it's somehow what is quite often assumed when you see such a specification in control flow is just the third possibility. The third possibility is that the actor executing A makes the decision whether A is doing or not. So the actor has the right to say, okay, I do the task or I forget it. Like Heinrich's travel application. I do it or I forget it and do it. Oh my goodness, that's not the way always. But that's a completely different way. So because then the whole control flow is totally wrong. It's not the semantics we specify. The semantics here says we make a decision here. We make a split. We either go left or we go right. If A has the right to decide whether A will be executed, it decides about the past. And that's not what is saying. Goodbye. So, how do we replace this? Well, actually, we make it simpler and remove this whole choice of third case. We just put in something there. We have B, and following B, we execute A, but A is optional. And it is the right of the actor associated with A to make this decision. So we have the deontologic rule saying that this is correct. The other one is a bit like it looks like maybe it's expressive of the one. Actually, if you take the semantics, literally, no. So I will go into more this so we can actually specify rules. Some of them we can also do some drawing. That has been a PhD thesis by Christine Hanschläger, who worked on this deontologic constraints in business processes. So basically, we define some deontologic action logic that controls the rights, obligations of our actors. So basically, we have four primitive constructs that do RA means the role, R has the right to execute the activity A. P to RA means that it is permitted that R executes A. F means it's forbidden, and O means it is the right. And I don't want to repeat the usual joke about obligations and forbiddenness. We talk about it. So, and then we can create the ontological formula by using the usual constructs, usual junctures to make it more complete. So if R has done function A, then another role or prime is permitted to execute action B and so on. Okay, I have 35 minutes left to this.
Plus 5 plus.
Okay, now, and then already coming to my last section, say exceptions. So, what is an exception? It's an overused concept sometimes, because you sometimes specify a particular branch that is a bit not so often you specify as an exception. No, I think this is not. It's part of the normal specification in it. Exception always refers to a disruptive event. Disruptive in the sense that we have to stop the normal process when this event occurs. We have to even roll back the target, undo something actually we have done, and then restart with some kind of different continuation. This is exception. So, and before I don't have much time for that, I would like to go back to number 27. I should have put a link here. It would be easier. 20 seconds. The law. So this was the complicated one. So we had this the split. We could do A, B, and C, and now we continue with D. And now let's get away with this A, B, C. Take this as a different name so to understand it. So assume we have some ordering process, and this is produce a part 1 of a product, produce a part B. This here is assemble it. This here is register all the production data. This here produce some kind of adornments for that one. For the adornments, they can be delivered separately, so deliver the adornments or put them together with assembly. And then here, just after checking, you create you want to add some specials. So you already add some specials to change the order assembly. Bit constructed, but because I did the ABCD and finally I tried to find some meaning for it, so to keep it simple. But if we have this there, and I don't use the priorities and the counters here, it makes it too difficult. As an example, so we have the exceptions here. As I said, produce part 1, produce part 2, produce accessory, register production data, assemble, deliver accessory. And now, let an interrupt event be that this is the result of some order from some customer as been done before. The customer comes in, changes, has some change. So, and say, let's assume that A, B, and D have been executed. So we have produced the accessory, we have produced part 1, and then we have already registered the production data. This is done. And then we decided E, so we deliver the accessory, but we don't put it together, so it can be assembled. That has been done, we stay there. Now comes the change. The change says, no, I don't want to have part 1, I want to have part 2. I want to have this or the other. This is another one. So what do we have to do? In this case, it's possible, when we actually undo the registration of production. It's a data storage file. We take this back, make a cancellation here, and we actually remove the dependency. Well, what has been done in part 1 has been produced, okay, take this particular thing and let's go and stop it. Because you don't have to use it all the time. There will be next customer who was like then remove the token that is going to the join gateway, indicating that we have done the production. But instead place a new token so that C can fire, so it's a production part B, part 2. But we don't have to do anything with this E, with the accessory. It can stay where it is. And then we can continue. So basically, we have, in this case, the following. Where was it? You get, for all the flow nodes we had so far, you get basically something, if not interrupted, then what we had specified. And then you have, if interrupted, we do what I just explained. If the event occurs, then we have a specific action returning back. And Then at some point we remove the interrupt. In this case, we just continue as normal. And the other case is if G, and G was the symbol, has already been executed by, then the reaction is a different one. You send a letter to the customer and say, no, we cannot handle this. It's also possible. Well, I skipped the part of the vertical model integration and said much more about me. And there are many things at the organization. So not only the vertical one, most of the things sketched on the surface anyway. Modularity, we will talk about that, which brings in some more subtleties regarding some processes that can replace activities. Multiple implementations, details of most of the ASM specifications that, apart from a very trivial example at the beginning of this sketch piece. Something on the verification, validation, this all has to be done. And of course, I didn't do this now. Further detailed extensions will also has not been done. When we have postponed or cancelled activities, this is actually associated always with the right connector. Then we have corresponding meta levels. I have the right to do something, and I can have the right to change also the process specification. A freeze concept. I can postpone activities, or I can already do activities that assume I have done my work. And adaptation to preferences, exception and negative changes. This is a project on that one. Okay, thank you for your attention, and I also would like to say thank you to all those who did most of the work in the project at SCCH. Felix Kossa, Verena Geist, Christian Bauer, Christina Maxwell, Christina Meister, Betsy Uwe and Freudenthaler. And last but not least, we're going to a little commercial break. Phase 1, for example, we published rigorous semantics of BPM 4.0. They are come out just a couple of weeks ago. And there will be a second part following this book on more detailed semantics of business processes, which will probably be published early next year. So just to make a advertisement here for this. And thank you again for your attention.
Thank you, Klaus-Dieter. We perfectly managed to have some time for questions, as you surely have.
My question is that abstract state machines are state-based machines, and you spoke a lot about action-based formalism. So, do you translate action-based formalism to abstract state machine, or you just use some combination of those two formalism?
The fact that they are state-based does not mean that we will not specify actions. Actually, the whole thing is about you have the condition and the action. Because the action is reflected then in also the changes to the state. And that an activity is triggered is just the means of the condition that is satisfied. In terms of expressiveness, well, I skipped this part. Abstract state machines. Well, there are these known work by Gurevich on expressiveness, the sequential ASMs capture sequential algorithms. We currently proved, was a different suggestion for a talk here, that we have a notion of concurrent ASMs and they capture concurrent systems like the ones we have here. And for the business processes, this is very much sufficient.
So state-based is the main.
State, if you have a state, if you try to get rid of the state, well, you actually don't get it. I just try to explain this for the message. There seems to be some belief that if you send a message, then you can get rid of any kind of state. if I send a message to you, I actually I give it to an agent, but abstractly I write into your message, into your mailbox. And this is then, again, part of the state. So, getting rid of it, so you see some formal methods people they try to put everything, not to do anything of the state, and then you get this kind of messages getting longer and longer, and you just keep them somewhere flowing around without saying they are stored. We have the concept to say, okay, put it stored there and read it, and it's very simple. You can specify things always this way or the other way, but abstractly, mathematically, will be somehow equivalent. If
Okay.
Of course, I have several. It is mainly the basic concepts and your extensions of the basic concept, I'm rather interested in your formal interpretation of events. And the question is, what is an event perceived differently by, say, two different actors? One of them, the event has happened, or another hasn't.
okay, so you have, let's say, let me summarize this. So you have a particular event. So something has happened, or something outside this. And one actor notices that this event is happening. So you can see the say this is like the same. The other one doesn't. So, okay. I thought I'm talking about it. So, if you have this situation, basically the problem you have is that the data, the state you have, is inconsistent. So you have to be sure. So that is, of course, if you have a centralized memory, it doesn't happen. But if it is distributed, then of course you have to have mechanisms on a lower level of abstraction available to say if this event is here, you have to ensure the event is also noticed there. Otherwise, you have this inconsistency and you should not. And then you have
It's all about an open world assumption and subjectivity perception.
It's not about the open world in the sense that this open world that you allow any income. You only see your view of the world and the rest you don't take into account. But it is, if you have this event that it is needed in two different places, then it's part of the specification and the verification there to ensure that both actors get the same information. This is clear. You have some obligation to do this. If it's irrelevant, if it's irrelevant, or if you allow that an actor has some kind of freedom to decide on the action to do what he does with a particular event. So you say, I notify you both with a particular event, and you decide who cares, and he decides to stir up the world because of this event. Then, if you both have the rights to do that, this is again part of the specification there, then you do it. And you have to make sure, if you have to say, and then tricky things in your logical system, if you have the right to do the opposite, or he recommends you to do, then the consequences for the whole system, what you have to do. Abstractly, you cannot just say, that's how this is. You have to specify what the state of these also this discussion of bias. There are some tricky things with being too it's a big yeah, but I said
Is there someone else who wants to ask a question? Okay, please.
About verification. So you somehow you're using formalism which seems to be appropriate for carrying out verification, but is that automated verification, or do you have to do some interaction with some sort of proof assistant? Which part of your language is decidable? I could also ask it this way.
Automation and verification. It's a dream in computer science since the 60s or even older. And I think in the last 40 years we have learned about the very limitations about automatic verification. If you go, and this has been done with various case studies with programming languages, with models, and you do some kind of rigorous mathematical approach to prove certain properties, in particular the most critical properties of the system, you're usually much faster than trying to tune a theory prover doing the automatic mechanical approach to verification. You can also try to do this with a theory prover, but frankly said, dealing with sequential algorithms in a theorem prover is already a hard task. Dealing with asynchronous concurrent systems is a much harder task for that. And most theorem provers will ask you to put a lot of work in there, and the verification will not work. In none of the theorem provers, whether it's PBS, whether it's Isabelle, whether it's KIF or anything, you will be able to complete a task without knowing actually yourself how you would like to do it. The theorem provers help you to not overlook certain aspects that you may think, or common mistake often done in mathematics. You look at something, oh, there's a trivial part, this is obvious, and then you concentrate on the difficult part and you complete the result there, but the mistake was in the trivial part. And the theorem prover may point out that to you, may show you, okay, you have to do something here, and then you see, okay, it was not so obvious. But to assume you have an engine and you throw your problem in whatever logic form you formalize it, and then after a while something comes out and says, yes, everything is fine, without you knowing what is happening there. This is a dream, and it will stay a dream. And unless you come to the boundaries of computability of the computing system, not only complexity boundaries, but also decidability and even completeness problems. And this is far more complicated than even the specification is already difficult enough. The reasoning about it is I wouldn't myself believe too much. We're working on theory proving and supporting tools for verification, but I also tell you that don't expect miracles. This is not in the scope of the program.
The time says now it's 11 o'clock, as you as actors are now entitled to enjoy a break. I am as actor now obliged to perform this activity to end this session. Thank you very much, in particular to Klaus Dieter again for the talk and for the answers to the questions and you for listening. And let's be back to the next session exactly at 11 o'clock.